So now we can talk about the standard normal distribution as a curve and as mathematically. So a continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram of the random variable has the shape of a normal curve, meaning bell-shaped. So essentially, we're looking at the relative frequency histogram and seeing if it's bell-shaped and symmetric. So we're going back to chapter 2 in the histograms. It all starts there, right? So now what we want to do is if we take a relative frequency histogram, every relative frequency for each category and each set of data is different. And this is like the randomization of samples, right? Sample variability. If I took one sample of SEC students and then took another sample of SEC students, those two samples will be different, right? Here's a sample. Let's say I took 30 students from SCC, and then here's another sample I took of 30 of SEC students. They may share no students, right? And let's say I took another sample of SEC students. Well, I may share some students, right? I may have selected the same, but they most likely are going to be different. And with different samples comes different means, right? And different standard deviations. So how do we compare? Well, if we went all the way back to when we first discussed z-scores and talked about distribution, we can remember that we used a standardized normal variable. And really what we used it for prior was to compare two distributions. So recall that it is the z-score is equal to the x value from the distribution minus the mean and divided by the standard deviation. And recall that the moment we randomize or standardize the normal variable, we have now just moved from this curve where we would have the mean and some sort of standard deviation, right, now to a distribution where it's a normal distribution and we standardize. So this actually goes from what the mean and standard deviation would be to where now the mean is standardized and we have a z-score of 0. And so anything to the left of the z-score, remember, is below average, and anything to the right of the z-score is above average. And that means when z-scores are negative, right, less than 0, that it'll be below average. And when these are positive, on the right side, they're above average. Okay, so let's go ahead and just quickly remind ourselves how to calculate these things, right? What is the z-score of x when x is equal to 1 and the random variable is the normal distribution with respect to the mean, 12, and standard deviation of 3. Okay, so I would just put z is equal to, right, the random variable x minus mu over the standard deviation. So over to the left, let's go ahead and list what we have. We know that x is equal to 1, the mean is 12, and the standard deviation is 3. So we would have the z equal to 1 minus 12 over 3. So then we just get something simple like negative 11/3, right? And we can always approximate if we need to as a negative 3.67. Okay, so what does this mean exactly? Okay, so z is negative. What would that mean, right? So then we could say, just as a note, right, since the z-score is negative, then x equal 1 is below average and to the left of the mean. So anytime when the z-score is negative, it just means it's below average and it's somewhere to the left of the mean. In fact, if I went up here, it would be like way over here. towards the tail end. Okay, so I took a distribution, right? Had a mean of 12, standard deviation of 3, and then I standardized it. Okay, so now let's go to an application. So Jerome averages 16 points in a competitive sports game with a standard deviation of 4 points. The random variable x is the distribution where the mean is 16 and the standard deviation is 4. So this means that the sports game itself has an average of 16 points per game, give or take 4 points. Suppose Jerome scores 10 points in one game where the z-score is negative 1.5 and when x is 10. Interpret this result with respect to the mean and in context of his competitive sport game. So let's go ahead and just write down everything that we have first. So if x is the random variable with the normal distribution of the mean of 16 and a standard deviation of 4, this means that mu is equal to 16, sigma is equal to 4, and then when Jerome scores 10 points, that's the x value. So x is equal to 10. So when they calculated the z-score with that, they got the z-score of negative 1.5. Okay, so we have all that information. Let's go ahead and interpret results with respect to the mean and then actually in context of the problem. So the first thing I would just say is so this will be mathematical, right? Like since since z equal to negative 1.5 is less than 0 when x is 10, this is below average. So now, if we want to do it with respect to Jerome and him scoring points in a competitive sports game, let's go ahead and now talk about it. So now we can say Jerome's score of 10 points is below average by 1.5 standard deviations. So when Jerome scores 10 points, that's below average because the average is 16, give or take 4. So in fact, one standard deviation away is 12 to 20. And so that's even more than just one standard deviation, it's 1.5. So if I went ahead and put this on a graph, let's say here's the standard deviations where z is equal to 0. So if z is equal to 0, and when we standardize, essentially what we call a z-score is a standard deviation because it's unitless. And so negative 1.5 would be, here's 1, 2, 3, 1, 2, 3. So here's like negative 1 to negative 3. So 1, 2, 3. That's like the standard 1, 2, 3. Green, okay. And negative 1.5 is here. So this means that he's off to the left, which is below average, right, by 1.5 standard deviations. Okay, so z-scores, normal distribution, shape, spread, what does this all have to do with you, right? Well, let's talk about the properties of the normal curve and kind of integrate everything together. So the properties of the normal curve is going to be 5 properties in which we'll use and kind of keep mentally in the back of our head as we do this, because we got to remember these properties to make sure that we're doing the problems correctly. So here, if I drew a normal curve, not very good, but here we go. Okay, so here's the mean, right? Or in other words, when z is equal to 0. So the curve has inflection points where the graph changes curvature. So inflection points are just when the graph changes from upwards to downwards. So you could see here at the tail end, like some curves happening because at the top it's going down, and then towards the tails it kind of changes. It's not like an upside down U anymore. So it kind of tails off. Well, these points in which where it changes is actually one standard deviation from the mean. So here. So this is when you have one standard deviation, right, from the mean. Inflection points. Okay, and then the total area under the curve, we know this, right, is 1 just from the previous chapters. Area equal to 1. And the area to the left of the mean is equal to the area to the right of the mean, which is a half. So remember we said because it was 1 that it would be a half on one side. 50%, right? Because that peak is the median. And then it tails off to the left and to the right, but it doesn't pass the x-axis. So it actually has what we call a horizontal asymptote at x equals 0. And so it's at this x-axis, this curve will never ever pass the x-axis. So it just kind of sits really, it ends up sitting just really close to the x-axis, but it'll never cross it. And then the last thing is this beautiful empirical rule that we had discussed way back in chapter 2 towards the end. And we're going to actually get to use the empirical rule even further.